In our previous lecture, we talked about periodic orbits, or oscillatory solutions, in other words, for second-order autonomous systems. And we said that one of the main tools in order to determine whether a second-order autonomous system possesses a periodic orbit is Poincare-Bendixson theorem, which stated a set of conditions, if satisfied, guarantee the existence of periodic orbits for that particular system. Okay, and we said that those conditions were only sufficient, meaning that there could be certain second-order systems for which those conditions may not hold, but still they may have periodic orbits. And we didn't prove Poincare-Bendixson theorem, but we had an example to which we applied it and obtained the result that that system must have a periodic orbit. Okay, today we will see another example, and again for that second-order autonomous system, we'll show that the system has at least one periodic orbit, but we're going to do that without using Poincare-Bendixson theorem. And we'll use a different analysis method, which can also be useful in certain applications. Okay, so this is an example from the text. Consider the second-order system or a class of second-order systems, because we're not directly giving the exact equations, but we give a class of equations, okay, by putting some constraints on this function g. Okay, we don't explicitly define g, but we give what properties g satisfies. Okay, where g function is continuously differentiable and satisfies z. Gz is always positive, this product, for all non-zero z. Okay, for all non-zero arguments. So let mu of x, okay, a function where x is our state vector x1 and x2. Okay, that pair. U of x defined as 1/2 x2 squared plus gx1, where capital G is the integral of lowercase g in the following sense: gy equals from 0 to y gz easy. Okay. Now for this second-order system, where g satisfies the assumptions listed or the conditions listed, we are asked to do the following. A, show that b of x remains constant along the solutions of the system. Okay. And B, show that sufficiently small initial conditions, okay, norm of x0, every solution is periodic. Now, some of you may have recognized that if you choose g of x1 directly equals x1, let's say, then we have x1 that equals x2 and x2 that equals minus x1, and g of x1 equals x1, okay, that identity function satisfies the assumptions that should be satisfied by g, okay, and that is x1 that equals x2 and x2 that equals minus x1 is the state space representation of the normalized mass spring system with where n and k, they're both equal to 1. Okay, so x1 that equals x2 and x2 that equals minus x1. Okay, so that's a normalized mass spring system and it's LTI clearly, and we know how to obtain the solution for that. We know the solutions. So this, in a sense, is a generalization, okay, of that particular mass spring system. And for the mass spring system or harmonic oscillator, we know that every solution is periodic. And in the extension, the generalization of that problem, we still try to show that the periodicity is conserved, at least for the solutions that start close enough to the origin. And we're going to do that through this function, with the help of this function, v of x. Note that if x1 that equals x2 and x2 that equals minus x1, the normalized mass spring system, this would correspond to 1/2 n x2 squared. N is 1, okay, so we have 1 x2 squared, and this is kinetic energy, and integral of x1 is 1/2 x1 squared, and this would be the potential energy of the spring. Okay, so in the special case, this is the total energy in the system, which is preserved, and in this generalization, so that total energy function becomes this v of x. Okay, and then this is in a sense generalized energy for the system, and through that energy or generalized energy function, we will try to show periodicity. Okay, so in the back of your head, you should remember that this is a nice generalization of the harmonic oscillator problem. Okay, so let's begin from the first part, where we ask to show that this function, generalized energy function, is constant along the solutions. Okay, so one way to do that is obtain a solution explicitly, x1 of t and x2 of t in terms of the initial conditions, and plug them into that and show somehow, after certain translations perhaps, that v of x is constant, it's not depending on time. Now we can't do that in general because it's a non-linear system, and we cannot write explicitly the solution of a nonlinear system. But since we're asked to show that this function v of x is constant, we can easily do that, or we can easily attempt to do the following, that if this is constant, it means along solutions of the system, it means that its time derivative, when you pass x of t through it, must be 0. Okay? Time derivative equals 0, it means it's not changing. If it's not changing, it has to be constant. So what we're going to do is we're going to differentiate with respect to time. We're going to differentiate what? V of x of t. X of t being the solution of the system starting from some initial condition. And hopefully we'll show that time derivative equals 0. So v dot, okay, time derivative of v of x of t equals, okay, partial of this guy with respect to x2 times x2 dot is here, and partial of this guy gx1 with respect to x1 times x1 dot, and x1 dot is here, and the partial of capital G, since it's the integral of lowercase g, is g. Therefore, we can explicitly write v dot as follows. So we have x2 dot plus partial of capital G times x1 dot, and partial of capital G is lowercase g times x1 dot. Okay. So that equals what? For x1 dot and x2 dot, we look at the system equation. x2 dot is minus gx1. So here we have minus x2 gx1 plus gx1 times x1 dot. x1 dot is x2. Okay. So clearly, here we have the same thing, but the magnitudes are the same, but the signs are opposite. Therefore, this is 0. Okay. So regardless of the initial conditions, v dot is always 0. That means whatever your initial v is, that the value of v will be fixed at that particular point for all future time. So that implies, therefore, v of x of t equals v of x of 0 for all future time. x0 being the initial state, the initial condition. Okay. Now let's move on to b, where we will try to show that for sufficiently small initial conditions, every solution is periodic. Okay. First, let's try to use the properties of this function g, or observe the properties of that function g for our purposes. First of all, note that z, gz, always positive except for the case that z equals 0, means that g, or the image of g, visits only the first and third quadrants. Okay. On the z g plane, for instance. Okay. Let's write an example. zgz. This is the origin. Note that for each z, g will take some value, okay? And then z times that value that g takes, that the product is always positive. Therefore, for positive z, g of c must be somewhere here. For negative z, g of c must be somewhere here in the third quadrant, okay? And since g is continuous, the transition from this, the table of image here and the table of image here must be continuous, and therefore that means that the curve must pass through the origin. Okay. For instance, the simplest case would be a line passing through the origin, and if the slope of that line equals 1, then that boils down to the normalized harmonic oscillator that we mentioned in the beginning of the example. Okay. x1 equals x2 and x2 that equals minus x1. But in the problem we're considering g's, or we're allowing g's that are not linear also. We're allowing more general g's. Okay. z, g of c. Any g, for instance, something like this, is also allowed. It can maybe 1, it can decrease, but it can never become negative, okay, if c is positive. Or here, it can never become positive, where z is negative, and so on. Okay. So that's lowercase g. Now let's try to visualize what happens if you integrate that. You start integration from the origin. then the integral of lowercase g, capital G, looks like y 0 g of y. Something like this, for instance, for this. For g of z equals z, then it will be 1/2 y squared. It will be just a parabola going up to infinity on both sides. But for instance, in this case, if the area here, shaded area, below this curve, if it's constant, so that means it's not constant. I mean, if it's bounded, that means this is converted to some constant value, okay, capital G. It doesn't have to go to infinity, like in the 1/2 y squared case, okay. But all in all, it must be always increasing, even if it's converging to something, it must always be strictly increasing on this side and strictly decreasing on that side, okay. And it must be 0 at 0 for all capital G. So that is g of y is positive everywhere except the origin, y equals 0, and g0 equals 0, okay. And gy strictly decreasing on minus infinity to 0, okay, on the left, and g of y must be strictly increasing on the right path plane, okay, 0 to infinity. So this allows us to claim the following, which will be crucial for our analysis to follow. Okay. Now, since g of y is strictly increasing, so that means if you cut this image by a horizontal line above the horizontal axis, okay? And then if that horizontal line that you're cutting this guy with, if it's not too high, then it cuts this image exactly at 2 points, okay? One of them is here, the other is here, okay? Now, it's at 0 at 0, and initially it must move away from the origin, move away from the 0, so that even though one of the tail or both of the tails can be converging to some constant value, okay, but initially you can find a height that's tiny enough so that if you cut this image with that horizontal line, it will intersect this curve at exactly 2 points, okay. One of the points will be on the left and the other will be on the right. So what I'm trying to say is the following. Hence, we can find C bar a constant such that for each C which is positive and not greater than C bar, there exists a unique pair of positive numbers A, B, let's call that, such that G minus A equals G g of b equals your constant. Okay. So let me redraw g. Okay. This is y. This is g of y. This is the origin. Suppose it's something like that. Then you can find a C bar such that below that C bar, if you cut this curve with that horizontal line passing through this height of C units, it cuts or it intersects the curve exactly at 2 points. So one of them is on the left, the other is on the right. And this y coordinate for that point, we call him minus a, and this guy we call him b. Okay. Now that we have to be careful about this. We cannot just say that choose any c, and you can always find 2 points where the curve is intersected. You cannot do that because suppose that this tail is converging to something, even though it's strictly increasing, it may still converge to some constant height. And if you pick your C too high somewhere here, then that line will never intersect the tail on the right. Okay? But since initially it should move away from the origin, you can always find some height that's small enough so that when you cut the curve with that height of horizontal line, you can find those 2 points of intersection. Okay. Okay. Now, what does this have to do with the analysis to follow? It has to do with the following class, which is next. Once again, remember that eventually what we're trying to show is we're trying to show that the solutions, starting from small enough initial conditions for the system given, are always periodic. Okay? And to reach that conclusion, what we're going to make, how we're going to proceed is as follows. We're going to make simple observation after another simple observation, and then once we connect all those chains together, we're going to reach our conclusion. Okay, so those little steps are very easy to understand, but to see them as individual links in a complete chain would be a little bit perhaps difficult in the first encounter. So if you don't feel very comfortable with the analysis here, I'm sure that you will once you go over it twice, okay, in the second time. Okay, so this is our first claim that we will use eventually for our purpose. Claim is the following: there exists a positive number, let's call it epsilon, such that if the norm of the state x is less than or equal to epsilon, and unless otherwise stated, we will always be using the Euclidean norm. Okay, but in general, it shouldn't make any difference because the vector norms are equivalent to one another. Okay, this implies norm of x less than or equal to epsilon implies that v of x is less than or equal to c bar, and c bar is the c bar that we're talking here. Okay. Okay. Here goes the proof. And also, never forget that. E of x is, let me put it here, E of x is 1/2 x2 squared plus g of x squared. That's how we define, or how we've given v of x. Okay. Okay. So here goes the proof. Let us choose first a1 and b1, two positive numbers. B such that g of minus a1 equals g of b1 equals c bar over 2. And from the argument that we just put forward here, we know that such a1 and b1 exist, okay, because we're choosing our c here equal c bar 1 over 2. C bar 1 over 2 is clearly less than c bar, therefore c bar 1 over 2 is in that interval, and if it's that interval, you can always find two numbers, a and b, and this is satisfied. Okay, and those particular a and b that we're using, we're calling them a1 and b1, okay, for c bar over 2. Okay. So, and then let epsilon 1 be chosen as, or be defined as, min of those two numbers, okay, a1 and b1. In that case, we have the following. Note that for this epsilon 1, if y is smaller than epsilon 1, if the magnitude of y is smaller than epsilon 1, then okay, y must be necessarily in this interval from minus a1 to b1, because epsilon 1 is chosen as the smallest of the magnitudes, magnitude of a1 and b1. And that implies that g of y less than or equal to, okay, that is, for y less than or equal to, the magnitude of y less than or equal to epsilon 1 means that y is in this interval, or if in this range, and if it's in this range, then the value of capital G must be less than or equal to c bar over 2. Okay, now this c is now c bar over 2. This is a1 minus a1. This is b1. Okay, and if y is in this range, clearly because g is increasing here and decreasing here, if y is in this range, then g of y must be, the value of g of y must be smaller than c bar over 2. Okay, so that's more or less clear. And then finally, choose epsilon. Okay, so this is the epsilon that we're mentioning in our claim. Okay, so this, now we're getting closer to the end of the proof. Choose epsilon be the smallest of these two numbers. Okay, choose epsilon 1 or c bar. Which one is smaller? That must be our epsilon. Okay. And now, using the inequalities here, what we're going to show is that if x is less than or equal to epsilon chosen as such, then v of x, okay, defined here, cannot be larger than c bar. It must be smaller than or equal to c bar. So let's see how that will follow. Now, we have the following. X less than or equal to epsilon implies v of x less than or equal to c bar. So that's what we're trying to show. That's the claim. But the claim says that there must exist an epsilon such that for small enough state, Vx is less than or equal to c bar. And now, in this part of analysis, what we have done is we have chosen that particular epsilon with which this claim holds. And the claim doesn't care which epsilon you choose as long as you choose an epsilon and if it's positive. And our claim is that if you choose epsilon, such that it's minimum of epsilon minus square root of c bar, and where epsilon 1 is defined here, and c bar is given in the claim, then everything is okay. Now let's see why everything is okay. This is true because of the following. Okay. Now, we said that the norm that we're using is Euclidean norm. It doesn't have to be, but suppose that it is. Then, okay, we have max x1, x2. The maximum of the individual magnitudes is always smaller than or equal to Euclidean norm, which is x1 squared plus x2 squared. Okay. Okay, and this is less than or equal to epsilon. Okay, so this means the max x1, x2 less than or equal to epsilon means magnitude of x1 less than epsilon and magnitude of x2 must be less than epsilon separately. Okay, now let's elaborate on both implications. Magnitude of x1 less than or equal to epsilon implies that because epsilon is the minimum of these two numbers, it must be less or equal to both of them, okay? So clearly epsilon cannot be larger than epsilon 1. Maybe it's equal to epsilon 1, but in any case, if it's equal to this guy, then that means epsilon 1 is larger than that guy, and in that case too, epsilon is less than epsilon 1. So in either way, x1 is less than or equal to epsilon 1. So that means g of x1 is less than or equal to c bar over 2. Okay? Because if the argument of g is, the magnitude of the argument of g is less than or equal to epsilon 1, then g cannot be larger than c bar over 2. Okay, so we use that piece of information here. x1 smaller than epsilon 1 means g of x1 smaller than c bar over 2. And let's talk about the x2 part. x2, or the norm of x2, less than or equal to epsilon means, since epsilon is defined as here, x2 cannot be greater than square root of c bar. Okay. Now x2 is also smaller than epsilon 1, but for x2 part, we need that piece of information. Okay, so therefore we're going to use the fact that norm of x2 is less than or equal to square root of c bar. Okay, and that implies what? 1/2 x2 squared less than or equal to c bar over 2. If the magnitude is less than or equal to square root of c bar, then magnitude squared over 2 must be smaller than c bar over 2. Okay, and then you combine these two, add these two, note that this guy plus this guy is no other than v of x. Therefore v of x, the sum, must be smaller than, less than or equal to c bar over 2 plus c bar over 2, which gives us c bar. And that was what we were trying to show. Okay. Hence, v of x, which which is 1/2 x2 squared plus g of x1 by definition cannot be larger than c bar when x is less than or equal to epsilon. Okay, we can find such an epsilon. And how we can find such an epsilon is put here. Okay, now once our little claim has been proven, so we can now move on to, or get closer to, periodicity. Okay. Let's keep our claim here for a while. Now, we're going to make another observation, and that will be our last observation. In the end, we're just going to connect all the pieces that we have generated. Note that for each C in 0 C bar, the set of points that satisfy v of x equals c, v of x is here, 1/2 x2 squared plus g of x 1. That equals c. So that means you pick all the pairs x1, x2, okay, such that they satisfy v of x equals c, and you mark all those pairs, okay, all those coordinates, all those points on the x1, x2 plane. And here, and in the end, what you obtain must be a closed curve. So that's our claim here. The points defines a closed curve. Okay. It's not important, but let's me also write it that that curve is symmetric with respect to the horizontal axis, or the x1 axis. Okay. Okay. Now, why is that? Okay, so this is our v of x. x1 axis, x2 axis. And here we have y versus g of y, let's say. Okay. Okay, so this is x1, x2. Now what we're interested in is a set of points that satisfy v of x equals c, and v of x was 1/2 x2 squared plus g of x1 equals c. And this c is, that c is less than or equal to c bar. Okay, that means once you cut with that c, okay, this is c, then we know that, because it's not too large, we know that there exists two intersection points. One is here, the other is here. This guy we called it x minus a, and this guy we called it b. Okay, so that's g of y. And now that's g of y, function here, and here we have 1/2 x2 squared. The sum must equal the constant c. And now what we're interested in, all the pairs, x1, x2 pairs, such that they satisfy this equality. And we try to show that all those points make a curve. Okay. Now, suppose that this is the x1, okay? x1 versus gx1, we can consider that. Suppose that we subtract the candidate x1 equals 0. Now, if x1 equals 0, g of x1 equals 0, and then what we have is 1/2 x2 squared equals c. Okay, therefore x2 could be either square root of 2c or minus square root of 2c. Okay, so that means when x1 equals 0, this is a possible point that satisfies the equation. This is the other possible point. Okay. So what we have here is square root of 2c, and here we have minus square root of 2c. Okay. And then what happens is you choose some. Let's go toward right. You choose some other x1. Okay, somewhere here. Let's say this is our x1. So x1. We start from 0 and we're going toward right. Okay. If this is x1. This part of x1, and then this part is here. Okay. This is g of x1. Okay, so this distance is g of x1. G of x1 plus 1/2 x2 squared. Okay, g of x1 plus 1/2 x2 squared must equal c. Okay. Therefore, x2 for this particular x1, x2 should be or could be c minus gx1. Okay, and then you multiply by 2 and then take the square root. And then both plus and minus are possible because we have x2 squared here. Okay, and then you go further to the right, choose another x1, and that will give you another larger gx1. And then what remains here is c minus gx1 is this part here, and that's now your 1/2 x2 squared. And then from that you pull x2 until you reach b. Okay. Once you reach b, okay. Once you reach b, g of b is c. Okay. If g of b is c, then this cancels, c cancels, and what we have is 1/2 x2 squared equals 0. Therefore, in that case, x2 must be 0. Okay, so x2 is largest here, and as you go along toward b, it becomes smaller and smaller in a uniform way because g is increasing, and you hit 0 when x1 hits b. And if x1 exceeds b, then g of x1 becomes larger than c, and then if you take this to the other side, you obtain a negative number here. 1/2 x2 squared equals a negative number. There is no real solution. Okay, that means for x1 cannot exceed b. This is the farthest it can get when you go to right. And when you go to left, minus a, using the same arguments, is the farthest that you can get. So in the end, what happens is the following. Here this is b, and here this is, let's say, minus a, and all x1, x2 pairs make this closed curve. Okay. And this part, lower part, has the equation x2 equals minus 2c minus g x1 square root, and here this is x2 equals plus 2c minus g x1 square root. Okay, and this part is symmetric because of this x2 squared term. Okay, and now we're almost done. Once we have shown that for small enough initial conditions, the trajectories make closed curve means oscillations, okay, or periodicity of solutions. Now, why is that? Let's remember that. Okay. Now we're ready to establish periodicity for small initial conditions. Okay, by small initial conditions we mean choose the norm of x initial less than or equal to epsilon. Okay, and our argument or reasoning goes as follows. Okay, now choose initial condition less than or equal to epsilon. Okay, and epsilon is constructed in the proof of the claim. And that epsilon, if you choose the initial conditions, the norm of initial conditions smaller than epsilon, then it's guaranteed that v of x, okay, is less than or equal to c bar. V of x of 0 is less than or equal to c bar. And from part A, we know that V of x of t, so this is the initial V, initial generalized energy. We know that since V dot was 0, for all future times, Vx of t must equal its initial value, because Vx is now changing Vx of t. That equals Vx of 0. Okay. So that means x of t belongs to the following set. Set of all x such that v of x equals v of x of 0. Okay. Now, this set is a closed curve. Since v of x of 0 is less than or equal to c bar. Okay. Because c bar is our particular height below which there always exist two intersection points. Okay. And the existence of those two intersection points gave us this closed curve. Okay. That means the following. X1, X2. Now we're on the phase plane. This is 0. And now you started, let's say, from some initial condition, x0, and x0 is small enough, less than or equal to epsilon, and that gave us vx0 less than or equal to c bar. And vx of 0 is c bar, and from that part A we know that for all future times, vx of t must remain in this set v of x equals v of x of 0, and that set, because this is smaller than or equal to c bar, that set is a closed curve. Okay, so this is our x of t. Okay. Now, x of t always remains on that closed curve. Now, the question is, okay, it doesn't mean periodicity if it always remains on that set, but it does mean periodicity because it can never stop on that curve. Because if you check the equilibrium point of the system, there's only one equilibrium point of the system, and it's the origin. Therefore, while on this curve, because it's not on the origin, it should be always on the move. And it's only possible that it moves in a certain direction. It cannot move sometimes clockwise, sometimes counterclockwise, because due to continuity, if it sometimes moves clockwise, sometimes counterclockwise, it means that somewhere in the middle it has to stop. It cannot choose in between, okay? Because of continuity. It can never stop, it should always move in one direction, let's say, clockwise. And that means periodicity. Why it means periodicity? Because suppose we start from this point, we move in this clockwise direction, and after a while, after finite time, we have to reach here again, this point. But then since the system is time invariant, it doesn't remember past, it doesn't care what time it is, only it cares where it is, okay? So again, the same thing must happen. The same thing must happen means the same time must elapse for another cycle, and for another cycle, and so on. Therefore, the solution must be periodic. Okay. So the final observation, therefore, is this loop contains no equivalent point. So that implies x of t is periodic. Okay. Now, before we finish, let me emphasize once again the importance of choosing small enough initial condition. Suppose that we didn't choose small enough initial condition. Okay, we choose an arbitrary initial condition. An arbitrary initial condition meant that v of x0 is not necessarily less than equal to c bar. It's quite large. For instance, we're talking about, so suppose that this converges. Okay, and we're talking about something like here. Okay, and then again, this is our new c tilde, let's say, or v of x0. Again, let's try to obtain the set of points that satisfy v of x equals c tilde. Okay, we do the same thing that we here choose an x1 and figure out what remains, and from that figure out x2. Mark it here. Choose an x1, figure out the corresponding gx1, that figure out corresponding x2, and so on, and then mark all those points. Now, since in this case, in the first case, we have to stop at b, and at b, x2 was 0, and we cannot go further, because going further means that x2 becomes complex. Okay, that's not allowed, x2 is always real. But in this case, if initial conditions are large, and g has this shape, and c bar turns out to be that it never crosses on the right? It means that no matter what x1 you choose, okay, you will always be able to find some x2. So that this part plus 1/2 x2 squared equals c tilde. So that means there's nothing that will stop the moving to the right of x1, and this curve in that case should look like the following. Okay. On the left, suppose that everything is fine, because here we have an intersection. So here everything is fine. But on the right, what's going to happen is the curve will look something like this. Okay. It's not closed. It's not closed means that, again, the solutions must always remain on that level set. You start here, x0, and then x of t is going over there, and it goes and goes and goes on forever. Okay? Therefore, it doesn't come back to where it started. Therefore, we cannot talk about periodicity. So that's why we have to be careful about choosing the initial conditions small enough.